Assalamualaikum warahmatullahi wabarakatuh and good morning to our evaluators. So for the FSG311, we choose the topic effect of the Eutectic Solvent DES on the structural properties of polysaccharide film for food packaging. We are from class RAS 1205G and our supervisor is Madam Nabila Akmal Muhammad Zalani. Firstly, before we go further, let me introduce our members. There are 3 members in our group. Firstly, my name is Muhammad Ahmad Amisha bin Omar, and then my friend is Muhammad Syami Hisham bin Hashim, and the last one is Safia Batrisha bin Shamsul Bahar. Next, we go to the introduction.
Introduction. Food packaging relies heavily on petrochemical plastics, which cause environmental pollution due to their non-biodegradability. Tamarind seed polysaccharide, or TSP, is a promising bio-based alternative with a good film-forming properties, but it rigidly limits flexibility. This study used a green plasticizer, deep eutectic solvent, or DES, which is based on choline chloride and ethylene glycol, to improve TSP film flexibility and investigated the structural properties using FTIR analysis. Problem statement. There are 4 problem statements for this study. First, the rigid cellulose backbone of TSP limits its mechanical flexibility and processability for food packaging application. Next, conventional plasticizers previously used to improve flexibility are toxic and environmental harmful. Next, there is a lack of sustainable, non-toxic plasticizers that can effectively improve TSP film properties. Lastly, an environmentally friendly solution is required to enhance the flexibility of TSP film without compromising safety. Hypothesis. There are 3 hypotheses in this study. First, the incorporation of a green plasticizer, deep eutectic solvent or DES, based on choline chloride and ethylene glycol, will improve the flexibility of TSP film. Second, DES is expected to enhance intermolecular interaction within the TSP matrix. Lastly, this modification will result in observable changes in the structural properties of the film, as confirmed by FTIR analysis. TSP as a food packaging. Growing environmental concerns related to petroleum-based plastics have increased the demand for biodegradable food packaging materials. Bio-based polymers such as starch, cellulose, chitosan, and tamarind seed polysaccharide or TSP have attracted attention due to their renewability and biodegradability. TSP is a silyl-glucan extracted from tamarind usindica seeds and is known for its excellent film-forming ability, good tensile strength, and oxygen barrier properties, which are important for food packaging application. However, neat TSP films are inherently brittle. This brittleness is mainly caused by strong intermolecular hydrogen bonding between hydroxyl group along the polymer chains, which restricts chain mobility and results in rigid film structure. DES as a green plasticizer. To overcome the brittleness of TSP films, plasticizers are added to improve flexibility by reducing intermolecular interaction. However, conventional plasticizer pose toxicity and environmental concern. Deep eutectic solvent, or DES, have emerged as a green alternative due to their biodegradability, low toxicity, and cost effectiveness. Choline chloride-based DES shows strong compatibility with polysaccharide like TSP and can disrupt hydrogen bonding, increase chain mobility, and reduce brittleness. Despite this advantage, studies on the structural effect of DES in TSP film remain limited, highlighting the need for further research.
Now, the materials and apparatus that were used during this study are tamarind seed polysaccharide TSP, choline chloride, 1,4-butanediol, distilled water, deep eutectic solvent DES, petri dish, magnetic stirrer, oven, and FTIR instrument. For this study, tamarind seed polysaccharides or TSP were used as the main biopolymer to form the film. TSP was purchased from Tokyo Chemical Industry, Japan. To prepare the DES, we use choline chloride as the hydrogen bond acceptor and 1,4-butanediol as the hydrogen bond donor. All chemicals were used as received without further purification. Now we will get into the preparations of DES and preparations of TSP-DS plasticide films. The DES was prepared by mixing choline chloride and 1,4-butanediol in a molar ratio of 1:3. The mixture was heated at 80 degrees Celsius with continuous stirring until a clear and homogeneous liquid was formed. After the preparation, the DES was stored in a desiccator to prevent moisture absorption before further use. Next, the preparation of TSP-DS plasticized films. The TSP films were prepared using the solvent casting method. First, 2 grams of TSP were dissolved in 100 milliliters of distilled water at 80 degrees Celsius with constant stirring until a complete solution was formed. Then, the prepared DAS was added into the TSP solution at a different weight percentages, ranging from 1% to 4%, according to the sample designations. The mixture was stirred thoroughly to ensure good homogeneity. After that, the solution was poured into petri dishes and dried in an oven at 60 degrees Celsius for 24 hours. Once it dried, the films were carefully peeled off and stored in a desiccator before characterization. Finally, the thickness of each film was measured using a screw gauge. Next, let's get into the composition of film samples. This table shows the composition of the prepared film samples. Each sample contains 2 grams of TSP, while the amount of DS was varied from 0% to 4%. The samples were labeled as TSP for the control film without DES, the TSP DS1 to TSP DS4 for films containing increasing DS content. Moving on to characterization Fourier transform infrared spectroscopy FTIR. To investigate the structural properties of the TSP DS films, FTIR was used. This technique helps us identify the functional groups present in both TSP and DS and to detect possible chemical interactions between them. In particular, FTIR allows us to observe hydrogen bonding interactions that occur when DS is added to the polysaccharide matrix. The analysis was carried out using the ATR technique, which enables direct scanning of the film surface without additional sample preparation. All measurements were performed at room temperature. Each sample was scanned in the wave number range from 4,000 to 600 centimeters to the -1, with a resolution of 2 centimeters to the -1 and 16 scans per sample. Any shifts or changes in peak position in the spectra indicate structural modification in the TSP films caused by the incorporations of DS.
Next is our result. We have to 5 samples from our lab session. And then you can see here for the figure 1A, display the transparent and brittle of pure tamarin polysaccharide film. The brittleness of TSP is due to the formation of hydrogen bonding between the polymer chains. This observation was also reported by Hilmi et al. 2025 for the TSP film. As you can see for the figure B and figure C, when the DS was added at 1 until 2 weight percentage, the film was observed still brittle. But we can see here the brittleness is reduced and it formed a better film. And then for the figure D and E, the film is more better and the brittleness is also decreased until it becomes 0, and the stronger the change. The change becomes the stronger one. The flexible film only can be obtained when 3 until 4 weight percentage of the ES was added. This is probably due to the presence of the ES that occupy the space between the TSP chains and prevent the formation of hydrogen bonding, hence forming more flexible film. The same observation was also reported by Hilmi et al. 2025 when 0.4 and 0.8 weight percentage of choline chloride with ethylene glycol DES was added to the TSP matrix. So for the characterization method, we have used 2 kinds of method. First is FTIR, Fourier transform infrared spectroscopy, and then second one is to measure the thickness of our DS doppler TSP film. So for the FTIR, we can see here on the CH2 stretching on the 889, you can see the peak here. The CH2 stretching band observed at 2889 cm in pure TSP becomes significantly weakened and indistinguishable in the DES doped TSP film. This is suggesting that destruction of TSP chain packing and strong intermolecular interaction between TSP and the choline chloride plus 1,4-butanediol DES. Additionally, you can see here for the stretching at the CH2 bending on the peak 1377, which we can see here in the DS double TSP film, the CH2 bending region mostly near occur at 1370 exhibit and band splitting, forming a doublet attribute to overlapping CH2 bending, vibration from TSP and choline chloride plus 1,4-butanediol, indicating change in the local molecular environment. So you can see here the pure TSP1 doesn't have the doublet peak, but for the other TSP with a DS formation, you can see here they form a doublet. And then for the second one is we use micrometer screw gauge, which to measure the thickness of our DS dopplet TSP film. So you can see here for the pure TSP film, the thickness in micrometer is 0.14, and then plus minus 0.005774, and then for the TSPDS1, this DS1 is 0.24, and then TSPDS2 0.23, and then for the TSPDS3 0.16, and then the last one TSP-DES4 is 0.24. So we can see here the thickness also increase as we put the weight percentage of DS we put it is also increased. So that's why the brittleness is reduced, and then it more flexible and more stronger. So nevertheless, the reduced thickness of TSP-DS3 0.16 mm indicates either a more intense polymer DS interaction or better molecular packing, and consequently the restriction of swelling during drying. This finding in general demonstrates that this composition of DS is an important factor in regulating TSP film structure and thickness.
This study shows that DES is an effective green plasticizer for tamarind seed polysaccharide films. DES disrupts strong hydrogen bonding in the TSP matrix, increasing polymer chain mobility and improving film flexibility. In general, film thickness increased with DES additions, and FTIR analysis confirmed hydrogen bonding interactions between TSP and DES. However, at intermediate DES loading, lower film thickness was observed, suggesting stronger molecular packing. Therefore, optimizing DES concentration is important for uniform structural properties. Overall, DES plasticized TSP films show strong potential as sustainable food packaging materials, and future work is recommended to focus on mechanical, barrier, thermal, and biodegradability studies.